The simplest explanation for dark matter is just standing gravitational waves. It just makes sense that if we have a boundary here, then we can have a gravitational standing wave that's sort of held between these two nodal points, and then it's a perfect place for normal mass to just kind of normal matter to settle into these pockets where there's this gravitational potential. So let's take a look at some equations that might prove this. So we can see how well a gravitational standing wave is defined by this particular thing here, where h this is the metric tensor is equal to 0. This is the D'Alembert here. So let's figure out what that means. And we have the metric tensor is going to be equal to two different um, perturbations of the metric here, because clearly we have a perturbation of the metric, and we have one in one direction and one in the other direction. This is kind of how you would add up two different perturbations, um, and so you get this type of combination to with the amplitude here cosine e to the iwt. This is just a regular wave. I mean, we're just looking at regular metric waves. These are waves of the metric tensor of general relativity here. So we're just putting that metric into a sort of a waveform here, okay? And then now, this is the stress energy tensor. So we're giving it some sort of an energy, so an energy density, and this is how we can take it. We're going to take the derivative, partial derivative in both mu and v of both the inverse and the regular metric. Well, it's kind of how you have to take derivatives here, and you notice how we get a derivative of tensor basically. So you can see we're going to get the w squared here, the a squared here. This is just taking a double derivative of this wave, well, kind of like a double partial really. So that's why we're getting the cosine again, because first is going to be sine, then do it again, you get cosine. You're going to get the w squared, you get the a squared, and then this is just energy density. So we're going to set it equal to like an mc squared effectively, right? And here's the Poisson equation. So we got the Laplacian of the v gravitational potential, and we got 4 pi g. This is the mass. So we kind of have to convert this to mass. We're going to divide it by c squared. So now we're going to have the mass density. Kind of look at it over here if you want to. We can see how, I might have to actually highlight these, but you can see how here with the mass density, w squared, a squared, 64, because now we've multiplied it, I believe. No, we had to divide it by c squared. So you get the c squared on the bottom. What we're going to do is we're going to plug, I kind of got lost here, but we're going to plug this into the equation here, and we're going to get this type of thing. I'm going to replace the potential with that symbol. And so we're just going to plug this stuff in here. We get the w squared, a squared, cosine squared, divided by, the 4 is going to cancel with 32, and you get 8 on the bottom. The pi is going to cancel, the g is going to cancel, and you got the c squared on the bottom. All right. This is essentially just the sum of we're just doing one wave here, yeah? But technically you'd want to sum up more than just one wave, because you're going to have all the different types of waves and amplitudes from all the different types of gravity waves. This is like trying to get like an effective mass that's like constant in the background of the entire universe. It's like the whole universe added up here in terms of how much mass is being added by these gravitational waves. And it just kind of tells you that there's this constant mass out there that is clearly dark matter. The mass, the missing mass, that's like, I don't know, 30% or 27% of the mass that's out there. It's probably this value here. Um, okay, and so anyway, we can continue. Let's look at this equation we've sort of figured out right here. It's just a Poisson equation. We plugged in our effective mass. Um, Now we're going to take the Laplacian. So we're going to take a derivative of this potential twice, and then we have to sort of cancel out these r's in the background. Um, so I think what we did is oh yeah, we're using the average here. So we're going to divide this by 2 and just use an average instead of having the cosine term. Since these are waves, we can just take an average and use the half value. So that'll just be easier for our calculations. Okay, and so now we're kind of simplified to this situation here. We're going to take the derivative on the outside first. Well, we're going to integrate this. We're going to move all this stuff over. So we have r squared here. We're going to integrate it by the r divided by the 3. And then we kind of get this term here with a plus c. Okay, cool. It's simple. Let's go to the next step. At this point, we're just going to divide everything by r squared. So we're going to get this situation right here. We divided this by r squared. Okay, and at this point, we can have two paths. We can either go over here or we can go over here. It's kind of important to go this direction, but let's look over here first. We can integrate this one more time and we can get the uh, gravitational potential, I guess, of dark matter here. So this is just the gravitational potential of dark matter. Interesting. And then over here, we have the orbital velocity. So let's take orbital velocity to be our derivative of that potential. So we're going to plug this into here and multiply it by r. When we do that, we just get this, so r squared. And at that point, we're going to consider at very large radii, where galactic scales. And at that point, we don't care about this term, it kind of goes away to 0. And so we're left with this, which we can take a square root of, and now we're left with this situation right here. All right, WA over some square root of some stuff. And we have this R sitting here. So that's nice. Now, remember that we want orbital velocities to be constant. So in order for us to get this orbital velocity, we need the frequency of the gravitational wave to be on the order of the size of the galaxy, meaning that W has to be proportional to 1 over R in order for this to um, act like dark matter, because then it would give us a constant velocity. So if this were the case, we would get constant velocity. We can sort of tune our equation to say, okay, let's force W to be 1 over R-ish. And that's kind of right, because we have this. W is 2 pi f, and f is c over lambda. And so now we have that W is actually proportional to lambda, or 1 over lambda, which means that if we want this to happen, then all we need is a gravitational wave that starts from the point right here, which is usually the black hole. It's a great source for this type of wave. And we're going to send that to the radius point. All right. And then that's going to be the N1. That's the fundamental frequency of the gravitational wave. And after that, it kind of just doesn't really matter what else happens because all the other stuff is neglectable. So the only thing that really matters uh, is this first wave. It's the only thing that's going to really sustain. Obviously, everything else does have impacts too, but if we want the velocity to be constant right now in this particular situation, we just need the frequency to be of 1 over lambda, and that would be the radius of the galaxy. Um, or the diameter, I'm not really sure. I think it's the radius of the galaxy. So you need the radius of the galaxy to essentially yeah, that's what it would look like. So that's pretty cool. We've essentially have established uh, a way for gravitational standing waves to act like dark matter, um, forcing them into this particular uh, frequency, this particular mode right here. Okay, so that's interesting. This is the first video, or I guess the second video on dark matter, but I'm sort of finding these hints that gravitational waves are dark matter. So interesting. Anyway, thank you so much for watching.